All right. Today's topic is Stein variational gradient descent, which is a Monte Carlo method, obviously, but a very general purpose inference algorithm, which is great because it's a counterpart to gradient descent, which some of you might be familiar with, that we can apply in Monte Carlo methods. It's been put forward 2016 by Liu and Wang, and ever since has been state-of-the-art algorithm in Monte Carlo methods. So there's actually a couple of things that the paper takes for granted that we did not cover, and I tried to cut it down as much as I could, but there's some things that are really needed to understand what's going on in the paper. So at first, I'm going to go over 3 principles that, again, many of you might have heard about, especially if you're interested in machine learning in general, but if not, I will quickly go over them to give you a good perspective and also maybe to give you an intuitive understanding of these ideas. Then I'm also going to give you a refresher on the problem setup that we actually discussed the whole semester long, but it's been some time since we've had the last lecture, and so just a quick refresher on that. And after that, we're actually ready to dive into the theory. The main theorem is called Stein's identity, and after we sort of have that covered and have an idea of why that theorem would give rise to an algorithm, then we can actually talk about the algorithm, also see some examples, see some animations, and conclude whether or not it's good. All right, let's get started. So these are the 3 ideas that I felt are necessary to cover to get an idea about this. Gradient descent and kernels should be somewhat popular by now, I guess. Chi-L divergence, not so much. But again, if you've never heard about these, it's more important that you get an intuitive understanding of what is going on and why these tools are helpful and why one would use them, rather than getting into the nitty-gritty bits about it. All right, so gradient descent. Usually with gradient descent, you do have some real valued function, which is often seen as an error function of a model. So we're trying to build a model again. And usually this error function is defined over the parameters that we have for that model. And now if you do have a point, let's say A, we want to find a new point in which the error for our model is lower. So that means we would like to have a set of parameters which fit better to whatever we are trying to do. And to do that, we actually use the knowledge that the gradient of that function is pointing towards the steepest incline of it, right? So if we were to go into the direction of the gradient, we would actually get a higher error. And then what we're doing is we're actually going into the opposite direction. And so minus the gradient is going to be the direction in which the error is going to be lower. And of course, that's very dependent on how much you're going towards that. So we also include step size. This is this epsilon right here, which is usually very small. And so what we're doing, if we already have a point, is we're going a small step into this direction right here. And then usually, if our step size is small enough, we have an error that is smaller than was before. Right? So this is the idea of gradient descent, which is often used in machine learning. And if you have a visualization of this, basically wherever you start, you can use gradient descent to eventually find the local minimum. This is actually very crucial. Usually you have to fiddle around with the step size and also get a bit lucky sometimes to find the global minimum, so the best set of parameters that exists. You might get trapped in a local minimum. But this is the idea of gradient descent, and just to give you a quick idea of why we're using this today and why it's also part of the main topic. This is what we are going to be doing. We are going to have some sort of an error function for distributions. So we're going to have a target distribution that we're trying to approximate, and then we're going to use gradient descent to have a good approximation and to minimize this error function. That just as a general outline for what we're doing. So second up are kernel functions. They do seem a little complicated at first, but then again, try to get an intuitive idea about them. So let's say we have an input space, x, and a function defined on it. Then there's simply one property that this function has to have, to call it a kernel, which is there actually exists another space, which is usually called feature space, in which we can express our kernel function as the inner product of these vectors, right? And more often than not, this function that turns the points into the feature space doesn't even matter and is often not even known. But there's a bunch of theorems that say it will exist, and that's most often good enough to actually have nice properties for kernel functions, right? So we don't really care too much about this expression right here. We actually care about a kernel, which is one, and a function that we know is a kernel, and then we already know it has some decent properties. And still, kernels are very useful because of this expression right here, because it actually allows for an intuitive sense of what they're doing. So remember, the inner product of two vectors is actually 0 if they're orthogonal to each other, and is going to be somewhat related to the norm of the vector if you just plug in one vector by itself. And so if we have 2 points, x and x prime, the kernel function can be viewed as just a similarity measurement of 2 points, right? Because they're very unsimilar if they're orthogonal to each other, which would be right here, and very different. And they would be very similar if this kernel function is rather large. So if this feature space stuff and all this theory is a little odd to you, all you have to remember for now, or at least the very minimum that you should remember, is that the kernel function can be viewed as a similarity measurement between 2 points. And also the fact that we do have a feature space, which is usually of higher dimension, lets us solve problems in a linear way, which wouldn't be linear solvable in our input space that we started with, right? So this is an example of why kernels are helpful. Again, I don't know how many of you are familiar with machine learning at all, but this is a very classic or basic example in machine learning. So let's say you have 2 sets of points, and usually you'd want to have a classification algorithm. So you want some algorithm that decides the classes in a good way. And if you were to choose a linear decision boundary, that basically means you would want to draw the line somewhere in this picture and say on one side of the line it's class 1, on the other one it's class 2. And most obviously this is going to be really hard, if not impossible, to do it correctly for all points in this picture right here. And what we're doing is we're applying a kernel function, the Gaussian RBF kernel, which you can see right here. RBF stands for radial basis function, which basically just says that it's dependent only on the norm of the points that we plug in. And so if we do that, this is actually the image of what we're going to end up with. So this is three-dimensional all of a sudden, and in three-dimensional space, a linear decision boundary would be a hyperplane that we could just draw right here. And then we could say, all right, everything above it is class 2, everything below it is class 1. And we could actually solve this problem in a linear manner. Also, this is going to be the kernel that we're going to use for our algorithm later on. For now, it's not really clear how kernels are going to fit in, but it will be, I promise. Also see that this parameter h has to be chosen in some way. I'm also going to come back on that later on. All right, so that was the second preliminary knowledge that is sort of required for the paper, and the last one is actually quite easy, although I think most of you will not know about KL divergence. So the Kullback-Leibler divergence is a function that measures how different two probability distributions are from another. If you look it up at Wikipedia, it's usually defined like this. However, I rewrote it because I felt like this gives a better understanding of what was going on, and also this introduces a notation that is going to be used throughout the presentation. So this just means that right here we're going to integrate over the whole space x, and then we're going to go over and just draw x from the distribution Q. And this is actually the expected value if you draw x from Q of this expression right here. So this is a notation to keep in mind. Now about the KL divergence, why does it make sense to think about it as a measurement of how different two distributions are? Most obviously, if you would just plug in Q and Q, it shouldn't be large because Q is very similar to Q, and most obviously it's going to end up 0. And also what you can think about, if you have two distributions that are very, very different, then they're going to be not many points in which the densities are going to have similar values. So if we have x's that are drawn from Q right here, most of the time this logarithmic expression of p is going to be 0 and is not going to affect this whole expected value at all. So you can basically forget about it, and then what we end up with is just this expression right here, which is going to be some large value. So if they're very, very different, it's just going to be this expression right here, and it's not going to 0. And so there's it actually makes sense to think about it that way. And if you were wondering, this is actually going to be the function that we will be using as our error function for today. So again, we're trying to approximate a target distribution with another distribution using gradient descent, and this is going to be our error function that is going to say how bad our current approximation is going to be. All right, onward. Now this slide should seem familiar to you. What are we trying to do in general with Monte Carlo methods? Now, usually we have some continuous random variable, and it's taken some values, and we do have a set of observations. And now the question is, what's the distribution of this random variable? And we can use Bayesian inference to go about this. But the main problem that we encountered, especially in the first few lectures, is that most easy approaches have a problem with this part right here, this denominator, this normalization constant, because this is going to be really hard to compute in higher dimensions. So this guy gives us a lot of headaches, and we would love to forget about it. And this is actually the main thing about this algorithm, that with its technique, we are going to be able to neglect this normalization constant and just care about this part, which is fairly easy to compute. Also, remember that this part right here is not dependent on that x, but it's rather the same all the time. Still hard to compute, but the normalization constant is just there, and no matter what we plug in as x in front of here. So that's the problem setup. And before I go on, just to give you an idea of what is going to happen, I'm going to throw some theorems at you, and it's not going to be very clear of where these theorems are going to go. But I do promise that at the end of the theory part, it's all going to come together nicely and make sense. But for now, just bear with me. I'm going to stretch or stress what's the main takeaway after every slide, and what you should be focusing on. All right, with that being said, Stein's identity. So if we have a smooth density, and we also have a smooth vector function, then if that vector function phi is sufficiently regular, which means that it has some decent properties and some boundary conditions that it fulfills, then we can actually do a sort of transformation with the help of the Stein operator and this vector function that we have. Again, this is the notation that you saw earlier. So this is the expected value with axis drawn with respect to p. And you can see the expected value then under this transformation is going to be 0. Now, what does this transformation look like? This is the so-called Stein operator. And there's a few things that you can observe when looking at the Stein operator. Now, the first thing you can see is that the Stein operator most obviously is dependent on p, right, which is the distribution that we started with. So you can already assume that if we were to plug in not p, but another distribution, q, well, then this equation right here is very likely not to be 0. All right. Also, you can see you do have the gradient of the vector function right here. So this is actually going to be a matrix. So if we were to actually introduce a new measurement of how different two distributions are, we would want to have an error function that is one-dimensional. So if we were to say, all right, we plug in q right here, or right there, it doesn't matter, as long as one part is p, the other one is q, then we should go about the trace of whatever is coming out of it, and that would be a good approach. And then the other thing that you would see, given that we're sort of fiddling around with it to get an error function, that this part right here is obviously dependent on our vector function phi. So you would guess, well, if I plug in q right here, this is not going to be 0 probably, but how much is not going to be 0 is going to depend on our vector function. So we do have to think about what set of functions is this phi going to come out of, and what do we want it to be. But for now, the main takeaway is this equation holds, and it's probably not going to hold if we insert q right here. And this is what we're going to do on the next slide. So we are considering a new density called q. And then we're actually having the same thing, but again with a trace, so it's one-dimensional. And we know that this is probably not going to be 0. And now you can see that we chose this phi from some sort of an h to the power of d, and I will go over that in a second. This is actually something that I didn't include in the preliminary because I thought that functional analysis is not going to be very beneficial of understanding it if we actually go into the very definition of the functional space that we're going to discuss. For now, I feel like it's good enough if you get an idea of what this is going to be, and this is called the reproducing kernel Hilbert space. So this is where kernel functions come into play and actually start to be important. What's a reproducing kernel Hilbert space? That is the vector space of functions which can be expressed as a linear combination of our kernel function. So you can think of that reproducing kernel Hilbert space as a vector space in which the kernel function is the basis and all the other functions are just sums over that and linear combinations of it, right? And this is why we do care about kernels as well. So now we do have a set of functions which we're going to consider. And what we want is we want the maximum of this expression right here. So basically we are searching, we're skipping through all these functions which are in the kernel Hilbert space. And then we want that one which is particularly sensitive to how different Q and P are. So this should be a large value. And then this is called the Stein discrepancy, what we defined right here. And it has a good reason that we chose this set of function and the reproducing kernel Hilbert space, because for this expression, for the Stein discrepancy that we defined right here, this can be solved via some functional analysis, and we can actually find the function that maximizes this, right? So this phi star is the argument that maximizes the Stein discrepancy for two distributions Q and P. All right, great, you think. Where is this going to lead us, and why does that help at all? This is sort of the cut of what we needed to do beforehand, before this function actually can come in later and save the day. But for now, the only thing you should keep in mind is this function right here is the argument that maximizes the Stein discrepancy measurement, which is also yet another discrepancy measurement of two distributions. So this is basically another competitor, if you want, for our KL divergence. Don't worry, as I said, we're going to use the KL divergence as error measurement, but for now, this is all you need to remember about Stein discrepancy. Now let's actually talk about an algorithm and how we would go about building an algorithm, right? And this is actually a fairly easy approach that should seem a little familiar to you. One, because some parts of it are very basic parts of machine learning, and then other parts we actually discussed in the lecture. So let's start over again. Let's say, all right, we do have some set of distributions, Q, and we want to approximate the target distribution, P, and our error function, as I said, is going to be the KL divergence. So what we are going to search is the one distribution Q in Q that minimizes our error function, so that is, with respect to the KL divergence, very similar to our target distribution. And this is called variational inference, and this is actually where the variational part in the name Stein variational gradient descent comes from, right? And this seems like a very naive approach. You know, the big question obviously is, what set of distributions should we choose, right? If it's too big, it's going to be hard to find an actual solution and to find this minimum. But if it's a set that is too small, we might not end up with a good approximation. And again, the approach is I think, fairly simple, because we're going to do something that we did in the very first lecture, which is we're going to consider transformation methods. So we're going to discuss distributions that we can obtain by applying transformations. So you should remember this. We do have a transformation function of some sort, and then we have some reference distribution Q0, and all we do is we draw samples X from Q0, then apply the transformation and call the new random variable Z. And just for reference, we already know that the density is going to look like this. And for now, I'm going to denote the density with QT of Z. This is actually the main part about it. You don't really have to worry about this too much. Just know that this means the density of our new variable Z, which has come about, which we have obtained by applying the transformation T. All right, now we do have a set of distributions which are actually fairly easy to compute. And we want to minimize this. Now the question is, how are we going to minimize this? And this is actually the part where the theory we did beforehand is going to save the day. And this is the part where gradient descent comes into play as well. So let's say we don't go all the way. Usually we start with the reference distribution and then apply some sort of transformation, and we end up with whatever, a new distribution. But let's say we just take a small step. So if we have one point X, we're going to leave X there and then just apply another transformation with a small step size, and F is the actual transformation. Then we can compute the gradient again. And if we do compute the gradient of the KL divergence, which is, again, remember our error function, then this is equal to this expression right here. And this expression right here should ring a bell to you. So this is an expression that we've come about by now, or at least something that is very similar to it. And this is where the theory of Stein discrepancy actually kicks in. So we remember that for gradient descent, we would like to go into a direction opposite to the gradient, and then we would minimize our error function. So with what we know from earlier, we would know that this is a function, that's the argument that maximizes this expression right here, right? And this expression, most obviously, is very similar to that expression, right? So we get to the conclusion, if we forget about the epsilon for now, and say, right, if this right here is going to be our transformation, and with the other idea of the transformation being part of the kernel, reproducing kernel Hilbert space, because this is what we discussed earlier, right? Then if we take the gradient, this is going to give us the actual direction in which we're going to evolve our transformation, so F. So actually we're not trying to find a new set of points, X, but we're actually trying to find a new transformation that is better than the one before, right? So we started off with this one right here. And then if we were to do gradient descent, we see that this is minus the gradient. And remember, we always want to have that minus, so we don't actually go into the direction of steepest incline, but we want to minimize the error function. So this is actually a good function to apply in the next step. And this is what we are going to do. So our new transformation is going to look like this, just a step function. And then we're going to apply the solution that we obtained earlier, right? And then this is actually equal to a step of functional gradient descent in the kernel Hilbert space. This is actually a very crucial point. Gradient descent, as I explained it at the very start of the presentation, usually searches for some set of parameters and is done in some vector space in which we search for new points. But now this is a gradient descent in a function space in which the points are equal to functions. And with each step of gradient descent, we get a new function. And once you've understood this, it sort of makes sense what the algorithm should look like. So we start with some transformation, and then we know, all right, there's actually a better transformation that we could apply, and we would get closer to the target distribution. This again is the full expression that I already gave earlier. This was just written down as the Stein operator. And now this is the algorithm that we're going to end up with. So we're going to start with some reference distribution, just as we would do in a usual transformation method. These are, for some reason, called particles. I guess there's a physical explanation of why you would want to name them that way, but all right, particles. And what we're going to do is, you can already see, we can choose how often we want to iterate through this algorithm. But for each iteration, we're going to update each point of that of these particles and apply this transformation right here. And after each iteration, this transformation is going to look a little different based on the points that we already have. And now it actually makes sense that this only takes one argument and the other one is fixed somehow. You could have written that down right here to make it clear, but that would be a little many indices. So what we're going to do is apply this transformation, and this function is actually going to average over all the particles we have and compute this expression. And we're going to get into why this expression would work and what actually happens right there and why this is great in a second. But for now, this is what we're going to end up with. And in the end, our particles are going to approximate the target distribution, right? Whenever we decide to stop the iterations. And actually the simulation of that, now this is set up with 50 particles and a multivariate normal distribution. So the circle right here is the distribution that we're trying to approximate. And then the red dots are the particles that I initiated just in some neighborhood of it. Again, like the reference distribution shouldn't be totally random, but it should be somewhat already close to where we're trying to go. And as you can see, the covariance matrix and the SML value are fairly different. And now as we iterate, I hope my PC doesn't crash down with the zoom and the animation, but it seems to work all right. They slowly gravitate towards the target distribution. And then you can see they sort of wiggle around a little and actually line up quite nicely, especially at the outer boundary. And you do have a set of points that is nicely distributed over the whole density function, right? So you also have this outer set of points which are really giving you a good idea of how the distribution is going to look. And now to discuss again a little bit of intuitive idea of what is going on about these transformation that we're applying. There's actually what I found to be a very good idea behind them. Now, the first part right here is what we're going to discuss at the moment. This is the kernel function, and as you remember, this can be, for now, just be viewed as a similarity measurement. So this is going to be large whenever xj to the power of l, or this is after l iterations, rather, is similar to x. And now this right here is the gradient of the logarithmic density that we're trying to get at. So if you think about the density again, and think about what gradient descent does, this is actually going to go into high density areas, right? Because this is a gradient which points towards the direction of steepest incline of the density function, or the logarithm is not going to change that. And what this direction is going to do, it's going to point our particles towards the areas of high density. And so this is the gradational part, so to say, which is actually claimed as well in the paper. However, I wanted to be sure and actually did, again, the simulation, but only with this part. So I neglected this part for a second. And I started off with the result that we got on the earlier slide, right? So we're basically already set, there's nothing to be done. And now we apply this part right there. And now you can see what we totally don't want to happen, which is all the points are going to collapse into high density areas, which is not too bad for our estimated value, but really, really, really bad for our covariance matrix. And also it sort of lets the idea of multiple particles be a little bit ridiculous if they are going to end up in the same place anyways. So this would be really bad if we only had that part, which is why we also have that part, which is called a repulsive force, which also makes sense again, because this is the kernel, the gradient of the kernel, and is, as a similarity measurement, going to point points away from each other. So to be sure, I actually did that as well. So I neglected this part, only simulated that part. And what you can see is they're just going all over the place, destroying the beautiful solution that we already had. And this is no good as well. And both of these animations should give you an idea of what is crucial when using this algorithm. It's actually very important to choose your kernel function wisely. Remember that Gaussian kernel, this is actually using the Gaussian kernel as well that I introduced at the very start. This H parameter has to be chosen wisely, because if your kernel is too strong, your particles are going to be all over the place, and if it's too weak, they're going to collapse too much. Obviously, in this case, I sort of cheated, and this is not going to happen just because your kernel is not strong enough. But you can get like too much collapsing of the points or too wide spreading of the points if you don't set up the kernel correctly. That being said, once you have a good kernel, you're basically good to go. And the thing that we see also in the definition of this algorithm is the expression we get here is only dependent on our target distribution P with this gradient logarithmic part right here. So we can do just a little very, very, very easy math. Again, if we have some normalization constant that is actually not dependent on x, well, then the gradient of the logarithm is just going to check out and be irrelevant because it's a derivation that we are considering. And so we can forget about it in the first place, right? And this is why this algorithm solves the problem that I discussed in the problem setup that we had in the first lecture, actually, where we discussed like the naive transformation methods, which have their limits with that normalization constant, and that is hard to compute. We can now just totally forget about it and just plug in our part without the normalization constant. And this is good enough as an estimator to actually get a set of points that approximates this fairly good. So that's the upshot basically of the whole algorithm. This is why it's fairly useful, and that should be about it. This is the paper that I use. They actually do have some code online as well, and yeah, I guess that's about it.